In classical mechanics, we can specify properties of systems simply if we know their coordinates and their momenta or their velocities, because most of the properties that we're interested in are some kind of function of coordinates and momenta. Now, in quantum mechanics, it's going to be a little bit different because now we no longer have precise knowledge of position and momentum. Instead, what we have to do is use what we call quantum operators to measure those things for a wave function. So every classical observable that we can come up with must then correspond to a linear quantum operator. Now let's talk a little bit about what that means. All right, now the effect of an operator on a wave function is to measure some quality of the wave function. So I will often use A as sort of my generic quantum operator, and A is measuring some property that we can define classically, and so we need to be able to now write down what A would be for that given classical measurement, whatever that is. Now there's two that we are already familiar with, and one of those is position, which we can write as x hat, and x hat is simply multiply by x. All right, and it would measure for us the position of the wave somehow. The second that, of course, that we're familiar with is the momentum. Okay, and in classical notation, sometimes that's written as mass times velocity in the x direction, but we're going to go straight to momentum for the most part. And again, that particular operator involves multiplying by IH bar, or negative IH bar, and then taking the derivative with respect to x. So the momentum operator actually looks like this when we're dealing with functions that are written in coordinate space. Now I'll remind you that we've defined this thing h bar as equal to Planck's constant divided by 2 pi, and that I is simply the square root of -1. Okay, so it denotes that we have a complex number here. Now, these operators are a great place to start because, as I mentioned, in classical mechanics, we can basically depict almost all of the measurables that we're interested in as some kind of function of these things. So how does this work in quantum mechanics? Okay, let's suppose that we have some sort of potential function, which is usually a function of coordinates. So that potential function might be written as some potential function, which we denote as v, as v of some coordinate position. All right, well, in order to make this a quantum mechanical operator, we would simply substitute for every place where x appears, we would substitute its corresponding operator. Now you'll notice that I am using very regularly this notation where I put a little tilde or a little caret over the symbol that means an operator. All right, so this operator for position would now be substituted into that potential wherever it appears as a coordinate in classical mechanics. Okay, it's generally a fairly simple operator simply because the position is simply multiplying by x, so we would simply multiply by this function. All right, for this particular operation. But nevertheless, if we were to move to a different representation, it might be useful to know that this is how we make that translation. Now, a second function that we will typically be interested in is kinetic energy. All right, and we know that kinetic energy can be written in terms of momentum like this. So it would correspond to the operator 1 over 2m times the operator p squared. All right, so once again, we see that this translates into an equivalent form as long as we convert the coordinate in classical mechanics to an operator in quantum mechanics. Now we would simply plug in the form of this p operator, and whenever I have a square, that really just means two successive operations of the same operator. So I would have IH bar ddx, and another successive operation IH bar ddx. Okay, now the ddx has no impact on this constant, that's just a constant. So these come out as a factor of I h bar squared. And successive operations of a derivative result in a second derivative. So the net effect of all of this, and I'll put this in a special color, is negative h bar squared over 2m d squared dx squared. And this, in fact, is what we associated with the kinetic energy operator when we wrote down the Schrödinger equation initially. All right, so you can see that having a function of these very basic operators leads to a correct quantum operator just by inserting that operator in with the same function. Now this can be made more general. So for example, if I have a function that can be expressed as a power series. We can simply translate this into a quantum operator. What would be a good example? Well, I know that, for example, cosine x can be written as a power series that looks like this. Okay, it's just a long series of terms that has even powers of x in it. And in fact, if we wanted to write this in a summation formula, we might write it something like this. So it's n is equal to 0 up to infinity. All right, and we would have negative 1 raised to the n power, 1 over 2n factorial x raised to the 2n power. And in fact, you can show that all of these terms would follow this formula for n is equal to 0, 1, 2, 3, and so forth. All right, so this is a way to express the cosine function as a power series in x. So then if I wanted to write the cosine function as an operator, so I would change that x to an operator, we would simply take this same summation and instead of having x here, I would have x hat. All right, so that's all we would need to do to create the operator for cosine of x. And mind you that x raised to the 2n power would be simply x repeated as an operation, a total of 2n times, 2n operations. That's all that it means. All right, so we could similarly do the same kind of thing for p. If I had cosine of p here, I would just have the same formula, and I'll skip some of this notation, and it would just be p raised to the 2n, and this p raised to the 2n would be minus I h bar raised to the 2n, and then it would be the 2nth derivative with respect to x. So that would simply be, this would be a very high derivative as we, for higher and higher terms of cosine. All right, now let's go one step farther, but I'll need a new page, and talk about vector operators. Okay, so when we introduced our notation, we indicated that R was really a vector that included coordinates for x, y, and z. Well, there's another way I can write R like this. I can write it as a little vector I times the magnitude x plus a little vector j times the magnitude y plus a little vector k times the magnitude z. And what I is basically a unit vector on the x-axis, and j would be the same thing for the y-axis, and k would be the same thing for the z-axis. So this gives me a way of expressing these things explicitly as vectors, and I can do the same thing for different kinds of quantum operators. So for example, if I wanted to express x, y, and z as a quantum operator, it would look like x, y, z, and that would give me something that looks like this: x along the x direction, y along the y direction, and z along the z direction. But more importantly, I can do this for momentum as well. So I could define, if I have this as a classical entity, a classical momentum vector, I can express this as a quantum momentum vector operator simply by taking these three components along these directions and then write what each of these is in terms of its derivative with respect to those coordinates. So this would be minus IH bar d dx, and this would be along the x direction, minus IH bar d dy along the y direction, and minus IH bar d dz along the z direction. Now, I realize this is a lot to absorb all in one sitting. We're not going to be making that much use of this, but this will come in handy, particularly when we talk about angular momentum for systems that have some kind of rotational component that gives rise to angular momentum, because an angular momentum is a vector thing, and so its operator is a vector operator. So it's going to be very useful if we can break down the components in this way, so we can then use it to understand the properties of angular momentum as an operator.